Hi everyone. So we usually, when we talk about steam problems, right, steam related problems, we look at devices like pumps, turbines, boilers and condensers. So they are actually open systems. So when you look at open systems and you want to look at their energy equations, you're going to talk about the steady flow energy equations, the SFEE. Alright, whereby this is potential at inlet, potential energy at inlet, kinetic at inlet, enthalpy and heat transfer is equals to the values at outlet plus your specific work over here. But there are some cases where you are looking at closed systems. Okay, so what happens if you just want to look at a closed vessel of steam? Then you won't be able to employ the SFEE. Instead, then you go back to your non-flow energy equations, NFEE, which is simply Q minus W is equals to delta U. Okay, the capital letters indicate the system values, the small letters indicate the specific per kilogram values. Okay, so we're going to look at this case for two typical processes. The first one is your constant volume process. So for example, here we are at state 1, okay, and it goes straight up with no change in volume, okay, straight up to another pressure, another temperature, okay, at state 2 over here. So if that is the case, right, then I want to look at the energy, then I'll be looking at Q minus W equals to delta U. Okay, and you know that when the volume does not change, we can assume that there is no work done. So when there's no work done, this is 0. Alright, so end up, right, you can actually calculate for the heat that is being transferred just by comparing the internal energy. So for this case, U2 minus U1 will be equals to your Q. And U2, you just use the dryness fraction equation to find U2 over here. And you use the dryness fraction equation to find U1 over here, then you can find the value Q. Okay. Now the next process is a constant pressure process. So let's say if your closed vessel of steam is undergoing a constant pressure process and it expands in volume. Okay, when we talk about expansion and compression, we are focusing on the volume. Okay, so for this case, it does not change in pressure. Instead, it changes in volume, and of course, it changes in temperature. Okay, and you can use the same equation, delta U, right, over here. Only this case, I'm not sure if you recall, but we did say that the work done under a constant pressure process, in fact, work done under any process in the PV curve is the area under the process line. Okay, so W in this case, right, W in this case, right, is actually equals to pressure multiplied by length times breadth. Pressure multiplied by V2 minus V1. Okay, so delta U is U2 minus U1, right? So I can actually shift this term over to the right hand side. I will get U2 plus P V2, alright, minus this term will be like U1 plus PV1. Okay, in fact, U plus PV is your specific enthalpy, H2 minus H1. So this is how you will find your heat gain or heat change by taking the enthalpy at state 2 minus the enthalpy at state 1.